Last week we started discussion on OpAmp, which is an active element and it amplifies the voltage and current on a system. Okay, in general format of an OpAmp is in this form. We show it with a triangle and it has two inputs, plus minus, okay, plus minus, and one output. The output, of course, is called output. The inputs, uh, the positive input is called non-inverting input, and the negative input is called inverting input. And of course, like all active elements, the OpAmp needs external power supply to operate. So we have two power supplies, VCC and negative VCC, and so one is positive and the other is negative. Okay, as we know, the relationship between output and input is VO is equal to the gain times VP minus VN. VP is the input of non-inverting input and VN is the input of inverting input. And this one is the general relationship between input and output. And there are two important equations or rules for OpAmp. The first thing is always VP is V equal to Vn and IP is equal to In is equal to 0. These are true for the OpAmps with feedback. If we have the feedback in OpAmp, or VP is always equal to Vn, and the current going through positive and like negative inputs are equal to 0. Okay, so uh, we saw a non-inverting amplifier. Also, we have inverting amplifier and voltage follower that I will post it in my lecture. But today I'm going to show you two different type of amplifiers built by OpAmp. Summing amplifier, which we can call it adder, and differential amplifier, which can be also called subtractor. So using adder, we can add two signals. So if we have two signals, 5-volt signal and 2-volt signal, we want to add them and have 7-volt signal in the output. Okay, so we can use this circuit to add those two signals together. Okay, so the first op-amp we are going to discuss today is summing amplifier or adder. Okay, here is the circuit for an adder. We have an op-amp, inverting, non-inverting, resistor R1, resistor R2. Resistor R2 is connected to voltage source. Let's call it V2. and the resistor R1 is connected to a voltage source. Let's call it V1. And here we have VO, and there is a feedback from the output to the input with resistor RF. And we want to find the relationship between VO and V1 and V2. Okay, so, oh, by the way, I missed one thing. The non-inverting terminal also is connected to the ground. Okay, so the inverting input is called Vn, and non-inverting is called Vp. Okay, let's solve the circuit. First, we look to the two inputs, Vp and Vn, and see which one is known for us. What is the value of Vn? I don't know, because it's connected to V1, it's connected to V2, it's connected to the output. So no idea what's the value of Vn. What's the value of Vp? Vp is connected to the ground. So definitely the value of Vp is equal to 0. So always look for one of these two inputs which the value is known. It's very important, okay? So the value of Vp here is known. So, and it's equal to 0. Vp is equal to 0. So Vp is equal to 0. It's connected to the ground. But based on what we learned from the amplifier, from the OpAmp, we know that Vp is always equal to Vn. So Vn is also equal to 0. Now that Vn is equal to 0, here, the next step, we write KCL for this node. A KCL for this node. It's very important. So one of the nodes has a known value, and the other node we write the KCL. So let's write KCL for Vn. So we can say Vn minus V1 over R1. What is Vn minus V1 over R1? It's like the current leaving Vn to like V1. So we have one current here, and one current going to the amplifier. So one thing which is very important for us to know is that we know that this current is equal to 0, because no current enters to the amplifier. We know that In is equal to Ip is equal to 0. So because this current is equal to 0, we can say that this current plus this current plus this current should be equal to 0. Okay, so it's the way we write the case here. So what is this current? The voltage across the resistor R1, which is Vn minus V1 over R1. So this is the the value of this current. What is the value of this current? The value of this current that I highlighted, of course, is equal to Vn, the voltage of one side of a resistor, minus V2 over R2. Okay? And the same thing for the last one. This current has a value of Vn minus Vo over Rf. So because all these three currents are leaving the node, we say this one plus this one plus this one is equal to. So you may ask a question, how do I know the currents are leaving the node? It's not important if they are leaving or entering. So if they are entering, the result will be negative. Okay. So if I always mention that if we have a current like I is equal to 5, I can say I is in the other direction with the value of negative 5. Okay, so it's same. So we assume that all of the currents leaving the node and of course the total of them is equal to 0. What about this current? This current is equal to 0 because no current entering the OpAmp. Any question? If you have any question, just let me know in the chat box and then I turn on my speaker. Okay, now that there is no question, let's continue. So this current will like Vm minus V1 over R1 plus Vn minus V2 over R2 plus Vn minus Vo over Rf is equal to 0. Okay, so this is the equation. Vn, what is the value of Vn? Vn, we know that it is equal to 0. So Vn here is 0, Vn is 0, and here is also 0. So if we move the Vo to the other side of the equal sign, Vo over Rf will be equal to negative V1 over R1 minus V2 over R2. Or we can say Vo is equal to negative Rf over R1 times V1 plus negative Rf over R2 times V2. Let's assume this one is K1 and this value is K2. So we can say Vo is equal to K1 V1 plus K2 V2. Okay, and of course if R1 is equal to R2 equal to R, we can say Vo is equal to negative Rf over R times V1 plus V2. And we see that we have added these two signal. What about Rf over R, or what about K1 and K2? Those are the coefficients. Okay, we can change those values by like by changing the resistors. Okay, so we can change those values. So this one is the adder circuit using an OpAmp. Any question? Okay, no question. Okay, the next, so you might ask, what about this negative sign here? That's fine. I will say that this is an adder, but in addition of adding, just invert the signal. Okay, so if one of the signal is 5 volt, the other signal is 2 volt, and let's say Rf over R is equal to 1. Let's assume it's equal to 1. So the output will be minus 1 times 5 plus 2, which is minus 7. We added 5 and 2 and of course inverted. So this adder, in addition of adding the signal, inverts the signal. So in order to have like plus 7, not minus 7, we can just cascade one inverter to this signal, to this system. So after like calculating the output, we can connect it to an inverter, so the output will be like like positive instead of negative. Okay, so this one is the next discussion we will have, but for now let's just focus on this, the fact that V1 and V2 are added each other, so V1 plus V2. Any question? Okay. The next circuit is differential amplifier. Or we can call it subtractor. Okay, here is the circuit of a subtractor. We have our OpAmp, we have V1, the other part is R4, R3, plus minus V2, VO, R2, and R1. Okay, now I have a question for you. Who can tell me which of these inputs, Vp or Vn, is known? Which value we can just calculate directly without writing any KCL or any other calculation? Which one is known? Any idea? Because in order to solve the problem, we have to have Vp or Vn. Which one is known for us? Okay, let's discuss. The first, let's look to Vn. If I look to Vn, Vn is connected to V1 and VO. Okay, of course, I have no idea about VO, so I cannot like tell that I cannot say that Vn is known for me. What about Vp? Vp is not connected to a direct voltage source or the ground, but it has like a known value. How we can determine the value of Vp? The first thing we should know is that the current entering here is zero. Current entering to Vp is zero, okay? And if we look to the rest of the circuit, this part, if we look to this part, this one is a voltage source and two resistors. Voltage source and two resistors. If there was a current entering to the op amp, definitely we couldn't like find Vp. But we know that the current is equal to zero, so we can assume that here is open circuit. We can assume it's not actually open circuit because there is no current. We can assume that it's open circuit, and now we can say, now can you tell me how we can find Vp? Vp, we can find it by voltage division. So we can easily say that Vp is equal to R4 over R3 plus R4 times V2. So this one is the value of Vp. So Vp is known for us. Vp is like a simple voltage division. We calculated Vp. Is it clear? If you have any question, just let me know. I turned on my speaker. Okay, no question? Okay, so Vp is equal to R4 over R3 plus R4 times V2. Now that we have a Vp, we can say Vp is equal to Vn. We have a question. Why do we use R4 instead of R3? Because it's a voltage division circuit is something like this. This is like a circuit. Let me just divide in this way. This one is the circuit. We have R3 and R4. In the R4, the voltage across R4, because one side of the R4 is connected to the ground, and we want to find the voltage across the other part of R4, so we can say the voltage across R4 is the R4 over the total resistors. So if we use R3, we will find the voltage difference between this point and this point. Okay, it's a very good question. Just the question is that why we use the R4 over R3 plus R4, not R3 over R3 plus R4. Because if we use R3 over R3 plus R4, in fact, we will find the voltage difference between across R3, VA minus VB. But what we're looking for is the voltage at this point, okay, which is the voltage of this point compared to the reference point. So if we look if we look to these 2 points, we see that these 2 points are the voltage across R4. Is it clear? Okay. So it was very good question, but in the voltage division, we find the voltage across the resistor. Here we want to find VP to the ground. So we see that it is the voltage across R4. If we use R3, in fact, we find the voltage difference between these 2 points, which we don't need it. We need the voltage difference between this point and the ground. Okay, so it's the reason we use R4. Okay, so let's continue. So now we know Vp is equal to R4 over R3 plus R4 times V2, which is equal to the same as Vn. Now that we got to this point, it's time to write the KCL at this point. KCL at this point. How we find this point? This point is the point that the feedback is connected to the input. So which node we should write the KCL? The node that the feedback is connected to that node. If we go back to other example, the previous example, the same thing. If you see, we calculated KCL at this node. The feedback is connected to this node. Okay, so it's time to write KCL for that node. Of course, again, as usual, we know that this current is equal to 0. There is no current entering to the OpAmp, so we consider these two currents, and the total of them should be equal to 0. Okay, so we say Vn minus V1 over R1 plus Vn minus Vo over R2 is equal to 0. Okay, and we factor out Vn times 1 over R1 plus 1 over R2 plus minus 1 over R1 V1 minus VO over R2 is equal to 0. We move the VO to the other side of the equal sign, so we will have VO over R2 is equal to Vn times 1 over R1 plus 1 over R2 minus 1 over R1 V1. Now instead of Vn, we substitute with this value. Okay, so we bring this value and replace it with Vn. So we will have VO over R2 is equal to R1 plus R2 over R1 R2 times R4 over R3 plus R4 times V2 minus 1 over R1 V1. Or we can say VO is equal to R1 plus R2 over R1 R2 times R2 times R4 over R3 plus R4 V2 minus R2 over R1 V1. This R2 will be cancelled with this R2. So we will have VO is equal to R1 plus R2 over R1, R4 over R3 plus R4 times V2 minus R2 over R1 V1. Okay, now we see that one of these, let's stop here and go back to our previous example, which was adder. For the adder, if we look, we see that both K1 and K2 are negative. So if we factor out from the negative, we can say that V1 and V2 are added to each other. But here, if we look to the equation, we see that one of them is positive and the other is negative. Okay, so if we consider this one as a K1 and this one, I'm talking about this part, as K2, we can say VO is equal to K1 V2 minus, let's just switch these names because I want to, so let's just call it V2 K2 K1. Okay, no matter, just it's labeling. Okay, so it's not a big deal. So we can say it's equal to K2 V2 minus K1 V1. Okay, so if we set the value of the resistors in a way that K1 is equal to K2, K1 is equal to K2, and call it K, we can say VO is equal to K times V2 minus V1. We see that the signals were subtracted from each other. Okay, so and that's the output. Any question? Okay, now that there is no question, Let's do one example for subtractor. Example, part A. Find input, output, relationship. Part B, if VCC is equal to plus minus 15 volt and V1 is equal to 3 volt, what is the allowable range of V2 for linear operation of the OpAmp? Okay, here is the circuit. Okay, this one is the circuit. If you remember from the previous lecture, I mentioned that part B, part A, of course, asking to find the relationship, which is okay. Part B is talking about the allowable range. If you remember from the previous lecture, we said that in order for a OpAmp to operate in a linear range, the VO should be in between negative VCC and positive VCC. Okay, so it's very important. So as long as VO is less than negative VCC or is greater than negative VCC and less than positive VCC, it is in linear. What if the VO is greater than VCC? It's not possible. As soon as the VO reaches to VCC, the system will be saturated and VO will be VCC. So it doesn't go beyond VCC, okay, or negative VCC. Okay, first let's solve part A, which is finding the relationship. This one is a subtractor, and of course we can simplify the VP. VP is equal to 15 over 15 plus 10 times V2, okay, and it is equal to Vn. So this one is something we know. And then we write the KCL for this point, for this node. KCL. So we say Vn minus V1 over 10. I cancel those kilos and I will plus Vn minus VO over 40 is equal to 0. Okay, So we can say 1 over 10 plus 1 over 40 times Vn minus 1 over 10 times V1 is equal to 1 over 40 VO. Or we can say 1 over 40 VO is equal to, we substitute Vn with this value, so we can say 140 VO is equal to 1 over 10 plus 1 over 40 times 15 over 15 plus 10 times V2 minus 1/10 of V1. If we simplify this equation, VO is equal to 3 V2 minus 4 V1. Any question? Okay. Now at this point, we got the relationship between VO and V, so yeah, between VO and inputs. Okay. Part B. Part B says if VCC is plus minus 15 volt and V1 is 3 volt, what is the allowable range of V2 for linear operation of the OpAmp? Okay, so we can say if V1 is 3 volt, then VO is equal to 3V2 minus 4 times 3, or it's equal to 3V2 minus 12. Okay, and to operate in linear mode, we know that VO should be greater than negative VCC, smaller equal to VCC. So instead of VO, we'll replace it with 3V2 minus 12 less than equal to 15 volt greater equal to negative 15 volt. 3V2 less than equal to 27 volt greater equal to negative 3, or we can say V2 is equal to less than 9 volt and negative 1 volt. Okay, so this one is the range. I have two quick questions for you. If V2 is equal to negative 5 volt, what is VO? If V2 is equal to 10 volt, what is VO? Let's call it VO1, VO2. All of you just tell me in the private chat what is VO1 and VO2. Okay, just find the value of the output if V2 is negative 5 volt, and find the value of output if the V2 is 10 volt, and send it to me in the chat box. I got 1, 2, 3, 4, 5, 6 answers. Still waiting for more answers. Okay, let me say most of you said negative 27 and 18. Negative 27 and 18. I have negative 27, 18. I have negative 15, 30. I have negative 15, positive 15. I have 0, and these are the answers I have. I said that VO in any OpAmp circuits cannot go beyond positive VCC and negative VCC. It cannot be in beyond these two values. So if VO is supposed to greater than VCC, it will be VCC. It's not possible for VO go beyond VCC. If it is supposed to be less than negative VCC, it will be stopped at negative VCC. So our input, our output, because VCC is positive 15 and negative 15, cannot be more than negative 15 and sorry, cannot be less than negative 15 and more than positive 15. If you calculate VO for part 1, I'm talking about this part. If we calculate V2, and as you said, V2 is supposed to what is supposed to be what negative 5, so negative 27. V2 is supposed to be negative 27, but it's not allowable. The minimum V2, sorry, not V2, VO. The minimum VO is negative VCC. It cannot go beyond negative VCC. So this one is not correct. We said that the circuit will be saturated at negative 15. So VO1 is negative 15 because it cannot go beyond negative 15. What about VO2? VO2 is it's supposed to be 18. VO2 it's supposed to be 18, but 18 is greater than plus VCC, and as I mentioned, VO cannot go beyond positive VCC, so it will be limited to positive 15. Okay, so this one is not correct. VO2 is positive 15 and VO1 is negative 15. So it is a range. Let's say this is a voltage, and here is 0, positive VCC, negative VCC, and this one is the volt. As long as the voltage, calculated voltage, is in this range, just the calculated voltage is the answer. But if the calculated voltage is in this range, the answer is negative VCC. It cannot go beyond negative VCC. If the calculated voltage is in this range, the answer is VCC. It cannot go beyond VCC. I want, so I just see all of, let me just gallery. Okay, I want to see that all of you thumbs up if you understand this important point. Yeah, okay, it's very good. So because it's very important, we cannot go beyond those two ranges as long as we are in this range, everything is fine. If we move beyond those range, we are limited to these two values. Okay, so that's it, and it's for today. And next, in the next lecture, we will talk about OpAmp building blocks. Let me stop the recording.